In this section, we're going to take a look at the area of polygons and circles, and this is the makeup one that flaked out in class. This will look a little bit different than the ones I normally do. All the answers are already written in here. I'm just going to work my way through them to remind you of what we did in case you're looking at this and looking back on what we did. Area is the region or the space inside of an object. The number of overlapping squares is how we defined it. So area is measured using square units. So a square measuring 1 foot on each side has an area of 1 square foot, and we write it with feet with a little square on the outside of it. We read it as square feet. One way to do this is with a geoboard or dot paper, and so this is the image that we originally had. We've gotten them all filled in for our images. We had counted 17 whole squares, and then we went back through and we noticed that we see this one right here and right here that are in pink noted with a 1. Those two are each half of a rectangle, or a square rather, so they're combined to give us 1 right here, and then the green ones as well to give us another one, so we get 19 square units when we do it like this. A second way we had done it, and this is 2 images overlapping. Our image that we originally started with was the shape that's sort of in the middle here. I'll shade it in, and we'll shade it in pink. The image is actually right in here. Let me try that again. Let's make it a little bit of a bigger stroke. So our image is inside of here. And what we had done is we counted up all of the rectangles, actually not rectangles, but squares that were outside of this object, and then approximated them as well. The second way we did it is, you'll notice we came back later on once we had area of triangle formulas, and we found these different triangles that are highlighted now in orange and red and purple, and we have a rectangle over here in blue. And we took away all of those rectangles and triangles away from the big overarching outside rectangle. So the outside rectangle was a 3 by 4 rectangle, so had a area of 12 square units. And then we took away each one of the triangle areas and the rectangle and the corners area from it to get our 3 square units. We talk about the area of the square grid being the fact that there are 9 units inside of this, but we can also talk about that in terms of the area, in terms of formula. The length is 3, the width is 3, and 3 times 3 is equal to the 9 that we get on the inside. We had some different units that we looked at in this section. We talked about square feet being 1 square foot being 144 square inches, and you can see along the top how we derived that. Basically, we use the ratio for inches to feet twice since we have feet squared. We can do the same thing in the same manner for doing yards. We can also go from miles squared, or square miles, excuse me, into square yards or into square feet using the conversions we've had from before. We had these units of measurement as well for their square units. So if you think about your square kilometers, it's 1 million square meters. Square hectometers is 10,000 square meters, and so forth. And the reason that you're getting these, of course, is because you're multiplying them by themselves. So normally, square kilometers would be 1,000, but 1,000 times 1,000 is a million with the meters squared. We did a couple of examples with this. So we started out with 3,000 feet. We talked about the fact that we could get into yards one of 2 ways. We can remember the formula a couple slides back, or we can simply remember the ratio between feet and yards and apply it twice. So if we do it that way, which is what we did it before, we have 1 over 3, which is 1 yard to 3 foot. Again, we're putting feet on bottom because we want our feet units to cancel. And we do it a second time, 1 yard over 3 foot, 3 feet, and then we can cancel out our square feet. We can also then take a look at this. We have 3,000 across the top. We have 9 across the bottom. This is 333 and 1/3 square yards. To go from kilometers or square kilometers into square centimeters, we notice that from kilometers into centimeters, what we would need to do is move our value 5 times. But since we're moving it 5 times in linear measure, we double that and we move it 10 times in square measure. So this ends up being 3, let me see here, we had a million, but with 3,780,000,000,000 square centimeters would go, and this should go in this blank, but of course, it's kind of short, so I put it over to the side. You can also measure land. So the English unit for measuring land is acres, and there is no abbreviation for that. There's also the unit of square miles. It looks like, of course, miles squared. Excuse me. And then we have a metric unit as well for measuring land. We have the air. Its abbreviation is just a letter A. We have a hectare for HA, and then we have a square kilometer. Now, one thing I'd like for you to notice is that all of these measure area, but there is no square, if you will, on the A or the HA or on the acres. They already are a square measurement. So when you're talking about 640 acres or whatever acre measure, it is just acres, and that is a square unit. There is no acres squared. All right, so we did a couple of these examples. We have a square field. It has a side of 30 meters, and we did this problem in one of a couple of ways. So one way to do this is to find the measurement of the field in square meters first, and then to turn it into hectares. So that's the way that you see it done here first, is we took the 30 meters times 30 meters, that's 30 meters squared, and then we did the conversion from hectare, or from meters squared into hectare. 1 hectare is 10,000 meters squared. We end up getting 0.09 hectare. There's another way you can do it. You could actually turn the meters squared into other units to begin with. Now, part B is an example of how we did it in multiple different ways. So that's when we did find the value in different ways. So we have a square field with a sign of 0.3 miles. So you could take the miles and turn it into yards. That's what you see above part B right here. So the conversion from miles into yards is 528 yards. Then you could multiply 528 times 528 yards. The other thing you could do is you could take your miles and you could multiply the length of the field times itself. So you have the 0.3 miles times 0.3 miles. And then you could turn the miles into yards by using that conversion twice. Another option is that you could turn your square miles into the yard square by using the measurement of miles to acres. So 1 square mile is 640 acres, and then 1 acre is 40 yards squared. All of them will end up equaling the same value, 278,784 square yards. Now we had some basic area formulas that we derived last time too. The area formula of a rectangle, of course, is length times width. We talked about the area of the parallelogram is pretty much the same formula. It's base times height. The base is actually highlighted sort of in pink below, and then the height is labeled in H. And we talked about taking that sort of right triangle on the left-hand corner and moving it to the right-hand corner. And if we do that, of course, we have a rectangle, right? And the rectangle has the height H that we've already labeled in our diagram, and it has the same width as the shifted width of the base that we originally had. And then the area of a triangle is simply 1/2 of this image of a parallelogram. So no matter what triangle you come up with, and that's kind of what we did over here on the right-hand corner with the pink and the green triangle on the very bottom right here, is that I drew a triangle. I think I drew the green one when we originally did it. And then I simply extended parallel lines out to create the remainder of this parallelogram, which was the other half of the shape. We end up with a parallelogram. So half of a parallelogram, 1/2, base times height, which was the area formula for the parallelogram, is the area formula for the triangle. So if you take a look at this, you have two parallel lines, line L and line AB at the bottom. And what this actually tells us is that every triangle which uses side AB on the bottom as a side of the triangle, and it extends up to either any of these points along the top or infinitely many other points, these are all triangles, and all these triangles have the same area, which is a very interesting feature because, of course, none of them look alike. So there isn't any congruency argument about areas relating to congruent triangles. A couple other area formulas we have are the area of a kite. This is an interesting one. This is 1/2 of the product of the diameters, D1 and D2. You can see the diagram below shifting the different pieces of the triangle around so that you can actually see showing up, right, the actual parallelogram or rectangle in this case that appears. And the reason, of course, that it's 1/2 the diameter, diagonal, 1/2 the diagonal D2 is because the D2 is actually the full width of angles of triangles 3 and 4's height. So the half of that would be the actual height of our rectangle when it's reshaped. The area of a trapezoid is 1/2 height times base 1 plus base 2. Another way to think about this is that when you add the base 1 and base 2 together and then you divide by 2, you actually average the width, if you will, of a trapezoid. So sometimes you'll see it written as base 1 plus base 2 divided by 2 and then multiplied by the height. And then the area formulas of a regular polygon with n sides, a couple different versions of it are either 1/2 the apothem, that's A, times the perimeter, or you can think of that as being 1/2 of the apothem, again that's the A, times the number of sides, times the side length. So S is actually the side length and N is the number of sides. So the way that this is justified or talked about, described, is by taking your regular polygon and changing it into n-congruent triangles. And they're all going to have, of course, the same area, and then we add their areas up. So however many triangles we have, that would be the number of triangles based on the number of sides. That's the n. It's multiplied by the area of one triangle, and one triangle's area is 1/2 the base times the height. The base is S, and the height is A, the apothem. So we get these two different formulas, and then of course a shortcut way to do that is to recognize that if you added all the sides together, that would be S times N, you'd end up with the perimeter of your shape. So we did a couple of examples last time finding the area of these figures. On the first one we had an area of a triangle. We wanted the area of the triangle that's in black. Its base, of course, is 5. Its height is 3, so the height doesn't actually have to occur inside of the triangle. It's just the vertical distance down to the base. In this case, we ended up with an area of 7.5 square meters. Number 2, which is our trapezoid at the bottom, is to average the two bases together. So if you added the 10 plus the 14, you'd get 24, and half of 24, will of course would be 12. So the average base length is 12, and then 12 times 7, which is the height over here on the right-hand side, would be 84 square centimeters. Then you have your diagonal. Now, this one was kind of tricky looking, and we decided that what we were going to assume is that we were going to assume that the 6 centimeters was actually just the portion of the length right here, which it might not be, but we would be more careful when we are looking at a test or something like that to mark that clearly. So we assumed that it was that 6 centimeters right there, I believe, and then, no, we didn't. I apologize. We assumed that the 6 went clear to here to here. That's what we assumed. And then we did 1/2 of that length times this length to get our 24 square centimeters. And that's where we paused last time.